Hello everyone and welcome to lecture today. Today we'll be talking about integrating in new coordinate systems, so doing double integrals in new coordinate systems with a focus on polar coordinates. So you'll hopefully recall from a previous calculus course and also from our previous discussions about circles that polar coordinates are described as follows. So the polar coordinate transformation is giving the Cartesian coordinates as the following functions. X is equal to r times cosine theta, and y is equal to r times sine theta. For r greater than or equal to 0 and theta between 0 and 2 pi. And the main idea here is that this is a transformation of the Cartesian plane. So it's an alternative way of describing points in the Cartesian plane. The idea being that for a given point in the plane, x, y, any point can be described by two coordinates, its x coordinate and its y coordinate. And essentially what this corresponds to is a grid. This is the x-axis, this is the y-axis. And the idea is that any point can be uniquely determined just by giving its x-coordinate and its y-coordinate, which corresponds to the value of it along the x-axis and the value of it along the y-axis. Now, in much the same way, points in the plane can also be described via its polar coordinates. But the way that the polar coordinate system cuts up the Cartesian plane into individual boxes, like you see here in the Cartesian coordinates, or xy, the plane is cut up into rectangular boxes where any delta x, so change in x, any change in y, is given by a box of area delta A, which is delta x times delta y. So for fixed values of r, we have fixed circles of varying radius, and for fixed values of theta, we have straight lines. And so fixed values of the angle theta, remember the angle theta is the angle from the x-axis. We have straight lines for each fixed value of theta. So these two coordinate descriptions can be used to define the same point in general. Right, so any point xy can be described in terms of Cartesian coordinates or in terms of its polar coordinates, its corresponding values of r and theta, and vice versa. So the idea here is that we want to figure out how to properly integrate, take the double integral of a function in this new coordinate system. And we'll develop in this lecture a procedure for doing that, not just for polar coordinates, but in general for a general coordinate system. So before we do this, let's kind of take a look at the main difference, and what the main difference is going to be in polar coordinates. And in general, this is going to be true for any new coordinate system. In looking at these two pictures, you can hopefully see that the main difference here is that the shape of boxes in the new coordinate system in polar coordinates are fundamentally different than the shape of boxes in Cartesian coordinates. So if you take one of these coordinate boxes here, say, the shape of this box is directly determined by the boundaries of the box, the bounds in theta, as well as the boundaries of the upper and lower circle that define this box. So the idea here is that at all costs, in order to integrate properly in this new coordinate system, we have to take this into consideration. You'll remember that when we did the Riemann sums in Cartesian coordinates, it was based on the area, or delta Aij, of each small box in the partition, which is just delta xi times delta yj. In polar coordinates, we still have that we'll call the area of the ijth box in our partition, delta Aij, but this is determined differently because the shape of the box is different. And to get some idea of what this should be for polar coordinates, we can use a nice idea that we have from a previous calculus course, which is that's the formula for the arc length of a circle. You'll remember that delta Aij, or I should say the arc length of a circle, for any segment of a circle, if you take, say, some segment of the circle right here, call it r, the radius of this segment of the circle is rj, and the arc length of this segment, call it delta sj, is going to be equal to rj times delta theta j, where delta theta j is the change in angle on that segment. And so this means that delta Aij, or the area of this box, is going to be approximately equal to, not exactly equal to, but approximately equal to the change in radius along the box. We'll call that delta Ri multiplied by the arc length along this sampled segment, delta Sj. This is not an exact equality, but it's a good enough approximation. And so what this is saying is that the area of any of these small boxes, when we do a Riemann sum in polar coordinates, is going to be delta Ri times delta, we'll say Rj, times delta theta j, or Rj times delta Ri delta theta j. You'll remember that when we take the limit of the Riemann sum in Cartesian coordinates, we get that dA is equal to dx dy in the integral when we're integrating. What this means is that in polar coordinates, we expect that when we take the limit, so as the Riemann sum boxes get smaller and smaller and smaller, we expect that dA should be equal to r dr d theta. So dA, remember, is called the area element. And what we're seeing is that the area element in the double integral changes when we go to a new coordinate system. Right? In polar coordinates, the area element is actually different. It's not just dr times d theta, it's dr d theta times r. So this is going to be the important thing that we have to generalize, and we have to kind of develop a procedure to do this for a general coordinate system, because there are actually many different coordinate systems that are very useful in multivariable calculus for integration. So let's see how to do this. So a general coordinate transformation from Cartesian coordinates is going to take the following form. The general coordinate transformation from coordinates xy into new coordinates, we'll call the new coordinates uv, is going to be x as a function of our new coordinates u and v, and y is a multivariable function of our new coordinates u and v. Just like for polar coordinates, right? Our u is r in polar coordinates, and our v is theta in polar coordinates. And the function for the coordinate transformation is just x equals r cosine theta and y equals r sine theta. So more generally, we can think that a coordinate transformation is going to be, we have old coordinates x and y, and new coordinates u and v, and in general, x is a function of the new coordinates, and y is also a multivariable function of the new coordinates. So just like before, the coordinate curves for Cartesian coordinates are just straight vertical lines for fixed values of x, and straight horizontal lines for fixed values of y. And when we go to a new coordinate system, just like in polar coordinates, we're going to have that the new coordinates for the new coordinate curves are not necessarily going to be lines. So we can just draw kind of a general picture to kind of wrap our minds around this. The idea is that, let's say you have that the coordinate curves are maybe very, very very, very complicated. So kind of like this maybe. Say that this corresponds to our new, it's called the u-axis, when v equals 0. And then when you fix values of u, you get coordinate curves that maybe look like this. And let's just say that this is our v-axis. So the horizontally moving curves here are fixed values of v, and the vertically moving curves here, say, are fixed values of u. And these are the coordinate curves for our new coordinate system, say. Just like before, for any given point, take a point, say, right here. Okay, every different point, x, y, is also described in terms of coordinates u and v. But we have the exact same general problem that we did for the polar coordinate transformation, specifically that the small boxes in this new coordinate system have a different shape than a rectangle. They're not rectangular. So what we have to do is figure out exactly how to approximate the area of these small boxes. So the way that we do that is by using what we know about the partial derivatives and what we know from our previous calculus course, which is tangent vectors to curves. So whenever you have a fixed curve, you can construct the tangent vector to that curve. Specifically, for the position vector here, it's in 2D. So the position vector for any point in our new coordinate system, we have x as a function of u and v, and y as a function of u and v. And the z coordinate is 0. So we need to figure out a way of obtaining the tangent vector to the curve, and that's done by taking the partial derivative. We're taking the partial derivative of the position vector, or dr du, at a given point amounts to taking the x partial derivative with respect to u and the y partial derivative with respect to u. And this vector dr du at any given point, if you evaluate it, is exactly a vector that's directly tangent to the curve at a given point. So this vector right here is tangent to the curve at this point. Specifically, an approximation to the distance. If you take a small distance, delta u, or a small change in u, is the vector dr du times delta u. And this is just the increment in the direction of u. So this vector is a vector that's tangent to the coordinate curve at any given point, and approximates the length, the magnitude of this vector approximates the length of the coordinate curve along that line for small values of delta u. All of this is for small values of delta u, and then we'll see small values of delta v as well. In a similar manner, the partial derivative of the position vector with respect to v is going to be the vector dx dv dy dv, which means that the vector that's approximating for a small change in v, approximating the length of the coordinate curve, is exactly the vector dr dv times delta v. This is a vector that's tangent to the coordinate curve in the direction of the v axis. Well, this is a vector that's tangent to the coordinate curve in the direction of the u axis. So up in the drawing here, I'll highlight exactly in each individual color here, you have that the vector dr du times delta u is this red vector right here, and the vector dr dv times delta v is this vector right here, so it's the blue. So we have at any given point, you can calculate these vectors, and we have that for small values of delta u and small values of delta v. We need to figure out a way of getting the area, or approximation to the area of this new box in this new coordinate system. And you'll remember from a previous calculus course where hopefully you went over what's called the cross product, the vector cross product, that this can be directly obtained by taking the magnitude of the cross product of these two vectors. Specifically, if you have a given at a given point, and you want to figure out an approximation to the area delta aij for one of the we're doing Riemann sums, say, and we want to figure out delta aij in our new coordinate system. This is exactly going to be equal to the magnitude of this vector, the tangent vector, to the coordinate curve in the u direction, which is dr du delta ui, say, cross product. So this cross right here is the vector cross product. So the magnitude of the vector cross product will give us this approximation to the area. And one of the nice things about the vector cross product and the magnitude of the vector cross product is that using the properties of it, we can actually factor out this delta ui and delta vj to get that this is the same thing as just the vector cross product of dr du with dr dv. That's the magnitude of this vector multiplied by delta ui delta vj. And to be accurate here, I have exactly equal to, but we should actually just make this an approximation, because it's really just an approximation for small delta ui and small delta vj. But in the limit, this becomes exact. So it turns out that this is the key towards going through and getting what the area element turns into for a double integral. It's this approximation right here. Specifically that in the limit, as the partition gets smaller and smaller and smaller, or the limit as delta ui and delta vj go to 0, we end up getting that exactly dA at any point, the area element at any point will be equal to the magnitude of this cross product times du dv. And this is exactly for any general coordinate system or coordinate transformation how we need to change and update the area element in the double integral. Now you can go through and calculate this out in general, but it's relatively straightforward to go through and do so using a little bit of your vector algebra. So what we know about the cross product. But what I want to do right now is kind of give you an alternative way of kind of viewing this, which is using what's called the Jacobian matrix. So the Jacobian matrix is essentially, you can think of it as, it's a matrix of the first partial derivatives of the coordinate transformation. So in some sense, we can think of this as the first derivative of a given coordinate transformation. This is just defined as the matrix that's constructed from dr du and dr dv. It's something that we can actually do, and we'll talk about a little bit more when we do coordinate transformations in 3D. But really all we need here in 2D is a 2x2 matrix. So it's the u partial derivative of x and the v partial derivative of x. That's the first row of this matrix. And the second row of the matrix is the y partial derivative of with respect to u, and the y partial derivative with respect to v. And a very, very interesting relationship between vector calculus and linear algebra is that when we calculate the determinant of the Jacobian matrix, this is directly related to that magnitude, the magnitude of this cross product. Specifically, that it's related to the magnitude of the cross product in the following way. So if we take the determinant of the Jacobian matrix and take the absolute value of it, remember that the determinant of a 2x2 matrix is going to be the product of the diagonal components. So dx du times dy dv minus the product of the off diagonal components. So dy du times dx dv. And what's really neat mathematically is that the absolute value of the determinant of this 2 by 2 matrix is exactly going to be it's the same thing. It's identical to the magnitude of the cross product of the columns. So here we're just drdu, we're using just the first two components of drdu because the third component is 0. Same thing with drdv. But these two things are identical to one another. So what we've shown is, in general, for a general coordinate transformation, that dA is the magnitude of this times du dv, which is the same thing as the absolute value of the Jacobian determinant of the coordinate transformation times dv du. And this formula can be used for any coordinate transformation to determine the proper way of taking the double integral in your new coordinate system. This works for any valid coordinate transformation. So that there are many, many, many useful coordinate transformations. There's polar coordinates. This is the main one that we'll focus on, but there's also what are called parabolic coordinates. There's you can generalize polar coordinates to elliptical coordinates. There's even what are called bipolar coordinates. The idea is that in each one of these coordinate systems, they take advantage of a different geometric symmetry in the description, and they're useful in a wide variety of scenarios. Bipolar coordinates are very useful for electromagnetic field calculations. If you look these up, there's a large number of different coordinate transformations, each one of which is useful in a different scenario. Oops, and I'm very sorry. I just realized that I have a small little typo here. The partial derivative here should be drdv. Sorry about that. But let's just go through and we'll try and apply this formula for our polar coordinate transformation to verify what we did at the very beginning, which was kind of an ad hoc way of getting the Jacobian determinant. So the Jacobian matrix for polar coordinates is going to be the matrix dx dr, dy d theta, or dx d theta, dy dr, and dy d theta. Which can be calculated using the definitions of the coordinate transformation. So dx dr is the partial derivative of x with respect to r, which is going to be cosine theta. The partial derivative of x with respect to theta is going to be negative r sine theta. Partial derivative of y with respect to r is going to be sine theta. And the partial derivative of y with respect to theta is going to be r cosine theta. So therefore, the determinant of this can be calculated relatively quickly. The absolute value of the determinant of the Jacobian matrix is just going to be the absolute value of cosine theta times r cosine theta minus sine theta times negative r sine theta. Which can be directly simplified. You have an r common to both terms. So this is going to be the absolute value of r times cosine squared theta plus sine squared theta, and cosine squared theta plus sine squared theta is just equal to 1. So the absolute value of the determinant of the Jacobian matrix is the same thing as the absolute value of r, and r is positive, so this is just equal to r, which is a direct calculation that gives us the value of this Jacobian determinant. And then from our general formula, which says that dA, the area element in the double integral, is the absolute value of the Jacobian determinant times dr d theta. We have that this is going to be equal to r dr d theta. And this directly verifies that the ad hoc calculation that we did at the very beginning of the lecture. Let's go through and do some examples of this and how to use this in different polar coordinate integrals. It's a very, very powerful tool because it gives us much easier integrations to deal with, both in terms of bounds and in terms of actually going through and doing the integral. So very often this will make doing integrals easier in the sense that it'll if we have this polar symmetry, we'll be able to get the integral of a function by using simpler methods, or more simple methods than we'd have to use doing the integrals in Cartesian coordinates. So very often, if an integral in Cartesian coordinates would have to be evaluated using, say, multiple trigonometric substitutions, doing a polar coordinate transformation will turn the integral from a trig substitution integral into possibly a basic integral, or maybe a u substitution, a much easier method in general. And that's kind of the idea behind a general coordinate transformation. So what we'll look at is the same problem that we looked at in the previous lecture, which is we ended up going through and getting the area of a circle. So in a previous lecture, we looked at the area of a circle. Say the circle has radius a. We want to, say, get an exact expression for the area of this region. So we know that the area of any region is given by the double integral over that region of the function 1. You'll remember that setting this integral up in Cartesian coordinates and actually doing the integral, you have to go through and do a number, if you do mainly it's that trigonometric substitution, which is pretty long. Turns out that if we just go straight to polar coordinates, dA is going to change to r dr d theta, and we have to determine the bounds of integration for this new region. Theta is the angle from the x-axis, So this is going from 0 to 2 pi. And r is going from 0, a lower bound, up to a for its upper bound. So you can already see that the integral we have to evaluate is much simpler, and the bounds are also simpler. And if we go through and do this double integral, you'll see that the function we're integrating is also much simpler. The inner integral is the integral of r, which is r squared over 2 from a to 0. So that's just going to be equal to a squared over 2 times the integral from 0 to 2 pi of 1 d theta. So this is equal to a squared over 2 times the integral of 1 d theta from 0 to 2 pi is just 2 times pi. The 2's cancel out, and we're left with pi times a squared, or pi times r squared. So we've shown that the area of r is exactly equal to pi times the radius squared, which is the exact same result that we got when doing the integral in Cartesian coordinates, but we got it at much less cost. Right? It's much easier to evaluate. This also makes that the volume example from before, the volume of a sphere, say, much easier to calculate. So the integral for the volume of a sphere in Cartesian coordinates ends up being relatively complicated. It's so complicated, in fact, that I didn't bother doing it in the lecture on integrating in Cartesian coordinates, because it takes a while. You have to do 2 separate trigonometric substitutions. It's possible to do, but it's not a very nice procedure. It's not a very nice integral to evaluate. It takes almost probably 2 pages or so of math, 2 or 3 pages of substitutions. But you'll remember that the formula that we got was that the volume of the sphere, we'll call it omega, and let's draw a picture out of this sphere. We'll call it a sphere of radius a. So this is a sphere of radius a here. The volume of this region was the double integral of the top surface minus the bottom surface, which ends up being 2 times the square root of a squared minus x squared plus y squared dy dx. This is the integral over the region R, which is the circle in the xy plane, just the trace of the shape at z equals 0. So this integral, remember, the bounds are relatively complicated, and going through and doing the trigonometric substitution here is relatively complicated. When you have to do this integral right here, it takes a while in Cartesian coordinates. But the idea here is that in polar coordinates it becomes relatively straightforward. So in the xy plane, remember, this region R is the circle of radius A. You always want to consider the traces when figuring out the bounds. But for this region, our bounds in polar coordinates are going to be relatively straightforward. It's going to be the well, our bound for theta is going to go from 0 to 2 pi. And our bound for A, or for R, is going to go from 0 to A. And then we have to update our function here to be in polar coordinates. So this will be 2 times the square root of A squared minus, then we have to think about what x squared plus y squared is in polar coordinates. It's just r squared, the radius squared. So it's a squared minus r squared. And this is multiplied by dy dx, or dA, which we know now in polar coordinates is r dr d theta. So this right here is the correct double integral that will give us the volume of this region. It's the double integral in polar coordinates now. You'll notice that this still looks a little like a long integral, a little bit long, but it's not nearly as bad as the integral from before. Specifically, right, this is an integral. The inner integral here is an integral that we can evaluate using a straight u substitution. The first thing is that this 2 will come out. And if we do a u substitution of a squared minus r squared, and remember du will be equal to negative 2 r dr. And actually, we don't even need to move this 2 out. This is the integral from 0 to 2 pi. And then the lower bound is when r is equal to 0. So that means that u is equal to a squared. And when r is equal to a, you get that u is equal to a squared minus a, which is 0. This will be times the square root of u. Then you have 2r dr, which corresponds to negative du. It's times negative du. So this negative sign switches the order of integration of this inner integral. We'll express square root of u as u to the 1/2. So this integral then is equal to the integral from 0 to 2 pi. The antiderivative of u to the 1/2 is going to be 2/3 u to the 3/2 from the bound a squared to 0. That's the inner integral. And when you plug in the bounds here, when you plug in 0 here, it gives you 0. When you plug in a squared, you get a squared to the 3/2, which is just a cubed. This is going to be 2/3 times a cubed times the integral of 1 from 0 to 2 pi, which is 2/3 times a cubed times 2 pi, or 4/3 pi times a cubed. Which is the exact formula you'll remember from maybe a high school geometry class, or the volume of a sphere. So you can hopefully see that this is a very, very powerful method. It's so powerful, in fact, that it can be used in a wide variety of applications. And we'll get into many of the engineering applications in the next lecture of the double integral. But anytime you have a double integral, you can use a new coordinate system if your domain is symmetric with respect to the new coordinate system. And it can help you very quickly get the correct value of the integral.